This time we're going to do example 4.7 from the book, which is a banked curve situation. And they're describing, or they're asking for how fast the car would have to move so that no friction is needed to prevent it from sliding sideways off the raceway, meaning either sort of into the center or, just by its inertia going so fast that it goes in a straight line and goes off the track that way. So we have a picture, but let's draw it larger. And let's try to draw a 24-degree angle here. Here. Okay, so we have our car, as you can see from the rear view. We're treating it like a point-like object and just identifying it as a solid thing. Not that one tire is going to come off the surface first or anything. Okay, and so the forces on it, it says no friction is needed. So we're going to imagine that there isn't a force of friction, like it's an icy track. Okay, and so then we would have a force of gravity, and then the only other force would be the normal force, which would be normal to the surface. So if I try to draw this, okay, and we would be in this very special situation where the y component of the normal force, meaning that I'm using the regular XY axis this time. So y to me means along that axis, and then x means along this axis. So in that situation, we're looking for the y component to be equal to the force of gravity, I'm sorry. And so this is the normal here. Okay, and it has a component to cancel with gravity that, like we were just saying, and then it has an x component that will help provide the centripetal. It will be the only source of centripetal force to get the car to go around the curve. Okay, so if I draw those separately, I have an x here and an ny, and I hope I drew it to scale so that it's the same. Well, the ny should be the same magnitude as gravity. Okay, now if you thought about it, like, well, what would happen if the car wasn't moving at all, right? And there's ice here. Well, it would end up sliding down the ramp, and the reason is that although ny and fg cancel, there's still an nx here, and so that causes an acceleration no matter what. And so if the car isn't moving at all, that acceleration in ends up meaning that the car ends up sort of, it's, accelerating in that direction. But then as soon as it leaves the surface, it doesn't have normal force anymore. And so also it gets pulled by gravity down. And so it would, come in and down too. If the car goes too fast, then that force nx is not large enough to match what the acceleration is that the driver's trying to achieve, and then it'll end up going off the track because it doesn't have enough force to keep it with that acceleration in a circle like that. Okay, so this is a very special situation, and the the acceleration has to match the banking of the curve at this specific angle. So really, if there was truly no friction, there would be only one speed that would go with this bank. Okay. But in any case, we're kind of treating this like as sort of a safety factor that they bank this curve um, to help. And then, really, there usually is friction also to help keep it on the track. Flying off into the stands would be a really bad thing. Sliding down into the infield wouldn't, it would be bad for the drivers, but it wouldn't hurt the crowd of, thousands of people. Okay, so in this situation then, we can use the y direction to help us get an equation um, for normal force, and then we can use the normal force to get an equation for um, the net force and therefore the speed knowing the radius. Okay, so when we would want to, right, we're trying to find the v, the velocity. Okay, and the way we're going to get that is we're going to say, well, I know centripetal acceleration is equal to the velocity squared over the radius. Okay, and I'm trying to solve for v, but I don't even know AC yet. Okay, and I would know, oh, well, that's really being caused, though. The Newton's second law says that centripetal acceleration would be the sum of the forces in that direction, the radial direction, or toward the center, um, divided by the mass. Okay, well, so that would be great if I could get um, that set up, but that means that I need to know nx. Okay, well, they don't tell me that, but they do tell me the weight and the angle. And so I can use the y direction to help me get um, ny, use the trig to help me get nx, and that's when I get to solve for the velocity. So this is a multiple step problem. So let's start off with the y direction. So I'm using y direction to find ny to find nx later. Okay, so I know that from this situation, right, we're not trying to accelerate vertically. So we're saying in the perfect conditions here that the sum of the forces in the y direction would be 0, and that would be ny plus fg. Okay, um, so if I know that, oh, I'm sorry, only know n, right? So then I need to solve for ny. And that means that I can use this angle here as this would be the 24 right here. This is 24. This one is 24, which means that this one that I drew, okay, is 90 minus 24, which is 66 degrees. Okay, it's also okay to, you stick with the 24. All right, but the way I drew it, I'm going to use 66 degrees. So now I know, well, ny is really the hypotenuse, okay, normal force, times I'm using sine here to find the opposite of this 66-degree angle. Okay, so then I would do n times sine of 66 degrees plus the mass of the car times gravity. Okay, and that has to equal 0. So then I can say, in terms of m and g here, I could divide both sides, subtract n times sine 66 from both sides, and then divide. So I would get this formula, okay? And technically I'd subtract, and so I'd get negative, but then g is negative as well, okay? Because if you use g is negative 9.8, because it's down, but in the end, you get the the magnitudes are equal. Okay, so then I have a formula for n, which is great because now I'm going to go back to the radial or the horizontal direction, and I need to know this some of the forces in that direction. Well, there is only one force that points that way, and that is nx. Okay, so now I could say, well, let's set this up. So I'll switch colors here. Um, so now horizontal direction, that's where the acceleration is happening. Okay, so I know that, like I wrote up above, I have centripetal acceleration equals two ways to think about it. I have the sum of the forces, you know, it pointing to the center of the circle over the mass. And I also know that that has to be velocity squared over radius. Okay, since the only force I have in pointing in toward the center of the circle is nx, I'm going to substitute that in here. Okay, but nx is really the normal force times the cosine of 66 degrees, because this one is adjacent to my 66-degree angle. Okay, so that's the normal force times cosine 66 degrees over the mass. Okay, well, I also had, right, I had created a formula for n. So now I'm going to substitute this whole thing, right? That's going to come down here. That was the point of getting that, because I don't know the magnitude of that normal force, but I do have it in terms of the weight. Okay, so, ooh, and I see that I wrote that wrong because this is supposed to be 66, not 60. Okay, so let's bring that down here. All right, so if I have my mg, okay, over sine 66 times cosine 66, okay, all that over m, okay, and that has to be the velocity over the radius. What is the radius? Let's check on that again. That was 200 meters, so I could substitute finally in here, okay, so that I have 200 meters. Okay, now notice mass cancels. That's great. That means no matter what the mass of the vehicle is, that doesn't matter because it cancels out. And then I get to start simplifying here and actually plugging in some numbers. So if I get, I'm sure this is a trig identity, cosine over sine would be the reciprocal of tangent. So here, I just am going to type it 9.8 Okay, so on this side, I end up getting a centripetal acceleration of 4.36 if I keep a couple sig figs. That's in meters per second squared. and then finish the algebra here. Make sure you take the square root to get the velocity. Okay, and you end up getting v equals 29.5. You know, your book rounded that off to 30. Okay, and that is the perfect speed to go with that bank to where the y components, well, the y components cancel no matter what, but that acceleration in the x direction is just the perfect amount to keep it moving around the curve without pulling it in. And it's enough to keep it from making a wider circle, basically going into the stands.